This is lecture video 41, and in this video I will explain cylindrical shells technique to compute the volumes of solid objects obtained by revolving some regions around axes. In the previous sections I explained disk method and washer method, where we slice our solid object into full disks or empty rings. But in these sections, we will be using circular cylinders to slice our three-dimensional objects. And it is a different technique to compute the volume and different way of slicing the object. And let me put a diagram here that summarizes all these three techniques for you. Volumes obtained by, let's say, volumes obtained by revolving regions. Okay, to compute such volumes, we mentioned two methods so far, and now in this lecture, I will mention the third technique. First method was the disk method, where we used full disks as the cross sections of our three-dimensional objects, and we use A of x, area of the cross sections, as the area of these full disks, and then we integrate this A of x to obtain the volume, right? Or this can be done in terms of y variable too. Everything can be written in terms of y too. Second technique was washer method, where we use not the full disks, but rings with an empty hole inside to slice our three-dimensional objects, right? This time, yes, there is this hole in the middle, and the cross-sectional areas are the areas of the rings. You are using outer radius, and inner radius, you take the difference of the bigger disk and the smaller empty disk inside to find the area of the cross-section, and then the same, you integrate this cross-sectional area. And now in this video, I will explain cylindrical shell method as the third technique. And here, we will be using not disks, not rings, but the circular cylinders of increasing radius to slice our three-dimensional object. So we will be using such circular cylinders, and the area of these will be our cross sections, and the area of it. Okay, let's say it is a cylinder with radius r and height h. So this is h, and the area, if you cut it up, and you will obtain this rectangle where this part will be the circumference of the base, right? So the area of this cross section now is the area of this rectangle, so 2 pi r times h, and then the idea of computing the volume is the same. You will continuously sum all those area of those cross sections. So if you integrate A of x with a definite integral like this, you will be finding the area of the whole three-dimensional solid. Okay, this is a very general summary of it. So let me try to explain the cylindrical shells method in a more detailed way. Okay, consider this example where we have this function and we are considering this region and we are revolving it. Revolve this region around y-axis, okay? Sorry, not y-axis, but this is the revolution axis, x equals 1 line. Okay, around x equals 1 line. So if you revolve it around this line, you will be imagining such a three-dimensional object, obviously. So this is your axis of revolution, not y-axis, but x equals 1 line. We want to compute the volume of this three-dimensional object. Usually, we learned some technique to compute this volume in theory. It is the Washer method, right? So you can slice. Okay, let me put the slices here. You can slice your three-dimensional objects into rings like this, so that these are your cross sections, and you can try to express the area of this cross section in terms of y, because this will be your inner radius, and okay, let's use green for the inner radius, and from center to here will be your outer radius. So you will try to express them in terms of y. Everything will be in terms of y because your slices, the cross sections are summed up through y-axis. So look at your curve. You need to find this hitting point on x-axis and this hitting point defined by this curve again on x-axis. What is this? These 2 points giving you the inner and outer radius. So you need to look at the equation of your curve and solve x in terms of y. So from this equation, is it possible manually to solve x in terms of y? So you see, we cannot solve x in terms of y. That's why in this case, in theory, Washer method is okay, but in practice, since you cannot solve x in terms of y, Washer method is not applicable in practice. That's why we need another method here. So we will use cylindrical shell method to slice our three-dimensional object in a different way. So how to do that? Okay, instead of taking horizontal rings like this, we will be slicing our three-dimensional object into circular cylinders, increasing radius like this. This will be your first cylinder. So for over another point on x-axis, you will draw another one, choose another point, draw another cylinder there. And here, for example, you will be drawing another cylinder, and you can imagine it, right? So by slicing your three-dimensional objects into circular cylinders of increasing radius like this, you can try to cover the whole solid object. Let me show you another nice picture about cylindrical shells method. So this is what you are doing while you are slicing your three-dimensional objects. For any x point, you put a very thin cylindrical shells and you try to cover the whole three-dimensional objects by using this thin cylindrical shells. It is like a paper roll, right? So it is also possible to slice your three-dimensional object like this into circular cylinders. So let's concentrate on this one where we draw over this xk point. Okay, so the height here is given by your curve, right? So this is the height defined by your curve. Remember, there was this curve, y equals 3x minus x squared. This is the equation of your curve. And over any xk point, the image yk is given by this curve like this. That's why, okay, this is yk given by this equation. And now you cut this cylinder up like this and you obtain this rectangle. And as we said, this is a very thin cylindrical shell, so it will have a thickness. Let's denote the thickness by delta xk. And so the circumference here will be 2 pi r, and the radius of this circular cylinder is what? What is the radius? We already choose the radius as this length. So it is what? It is xk. From here to here, it is xk, and there is this fixed distance here. So the radius is xk plus 1. So 2 pi radius, which is given by xk plus 1. This is the radius of your cylinder, and this is the height given by your curve, and there is this thickness. That's why the volume of this very thin cylindrical shell, Vk, is given by this formula. Area of the base, okay, so it is this length times the thickness times the height. So they are all here. Circumference is this part, height is given by the curve, and thickness we denote it like this. And to cover the whole volume by using this cylindrical shells, okay, what is Vk? It is the volume of kth cylindrical shell. And I can show you that kth cylindrical shell here in the picture. Now it is this orange one, and there are many of them like over each k point. The orange one is analyzed here, so its volume is given by this. And if you sum up all those volumes of any cylindrical shell, they are n many, because we consider here we are dividing this interval into k many sub-intervals. So from 1 to n, if you sum up all these cylindrical shells, you can try to cover the whole solid object. But see, as long as it is finite, like n, your volume is not totally covered. You need to send this n to infinity to get rid of those uncovered parts. So that's why the actual volume without sending n to infinity is approximately the sum of the volumes of cylindrical shells. But once you send n to infinity, then instead of this approximating sign, you can put here exactly equal sign. And you know, this is the Riemann type of sums where you can express it in terms of the definite integral. So you remember the interval of integration was from 0 to 3, it is here, okay? And then, so that's how you transform the sum of the volumes of kth cylindrical shells to the definite integral like this, okay, from 0 to 3. So if you compute this definite integral, this number gives you the volume of the solid object obtained by revolving this region around x equals 1 line. So it looks like this. We used very thin cylindrical shells to obtain its volume. So what you see here is this Riemann sum is expressed in terms of the definite integral, where this was the radius and this was the height and this was the thickness. And so in the integral, you see them again. So this is radius, this part is height, and the x corresponds to this part, where the thickness part. Okay, so the formula inside your definite integral goes like 2 pi times the shell radius times the shell height, radius and height. This is how you obtain the volume formula for the solid object if you use cylindrical shells technique, okay? So this is the important volume formula for us. Okay, let's, I think we understand all the details for the volume formula. So now we can write it in a very nice box, okay? So this is the radius, I will repeat, this is the height. So the formula to compute the volume of solid objects by using cylindrical shells technique, shells method, goes like this: 2 pi times shell radius times the shell height. So it can be rewritten as this formula, 2 pi r8 dx. Okay, so and this picture is a very nice picture explaining you the slicing procedure. So instead of using full discs or empty rings, you are using these circular cylinders to cover the whole volume, the circular cylinders of increasing radius. This is also another way of slicing your three-dimensional object. So here is our first example about Shell's technique. We have a region here and we are revolving this region. This region around y-axis. Okay, that's why you will obtain, okay, so if you revolve around y-axis, this is the axis of revolution, you will obtain something, sorry, some three-dimensional object like that, right? So, like this. Okay, something like this. So you imagine the three-dimensional object and we will be slicing that three-dimensional object into circular cylinders like this. So the center of this circular cylinder is here. That's why this part is the radius, which is x. And the height for any arbitrary x point, the height is determined by the curve, you know? This is the height of the cylinder and it is given by your curve x. So we have everything we need. By Shell's technique, we use this formula. From A to B, what is A, what is B? From 0 to 4, of course. These are the boundaries for your integration. 2 pi times Shell's radius times Shell's height dx. Here you see the three-dimensional version of this picture. So this is the height given by the curve, where your curve is square root of x. And this is the radius of your cylinder. You see, this is the radius. Let me write it. This is the radius, so it is x. And so let's compute the integral. From 0 to 4, 2 pi, radius is given by x, and height is given by your curve dx. If you compute this definite integral, you will find the volume of this three-dimensional object obtained revolving this region around y-axis. So what is the result? From 0 to 4, you can take 2 pi out from the integral because it is just a constant. You are integrating x to the power 2 over 3 dx, so it is 2 pi, add 1 to the power, divide by the same power, right? Like this. And there are boundaries from 0 to 4. If you insert upper lower boundaries, you will find this value for the volume. Okay, this is how you apply cylindrical Shell's technique. On the other hand, you can solve the same question by using Washer method. So recall. Let's solve the same question by using Washer method. So let me draw the figure again. I have this region, remember, and we are revolving it around y-axis, where this curve, equation of this curve is y equals x. After you revolve it, I obtain something like this. Okay. So this is the three-dimensional object, and I will be using horizontal rings to slice it, right? So this is how you can use Washer method to slice your three-dimensional object. And you see, for an arbitrary point y on y-axis, now this is my inner radius, right? So from here to here. So I need to find the exiting point for the inner radius, so R inner. It is in fact given by this curve. So this is y equals square root of x curve, sorry, y equals square root of x. So you can solve this curve in terms of x. X is given as y squared. So this point on x-axis is in fact y squared, which is the inner radius. And the outer radius, let's try to see the outer radius. This is the center of your ring, and from here to here, this blue line gives you the outer radius, and it is something always fixed as 4, you see? So this point is your outer radius, which is always the same, it is 4. So now I am ready to express the volume by using Cauchy method. It is the area of the rings from where to where. This time you need to be careful because you are integrating not over x-axis but y-axis. That's why you will look at the boundaries on y. From 0 to which point? So you see, this point is 2, from 0 to 2. So 0 to 2, and the details, outer radius, inner radius, we express them pi, outer radius, everything. By the way, everything is with respect to y here because we are summing up the areas of these rings through y-axis, a of y dy. So outer and inner radius will be expressed in terms of y, which we did here. So from 0 to 2, outer radius is 4 minus inner radius. Inner radius is y squared. There's another square here. Don't forget to write it. And if you compute the result of this definite integral, of course, you will be, you find the same result as they both give the area of the same solid object. So not 4, of course, 5. You will find the same result. So here, this is a nice example of which we solved by first using shell method on the right side, and then we used Cauchy method on the left side. Sometimes for some examples, you can use more than one technique, like we did here. Okay, let's move on to this example, which will be the last example of this lecture video. This time, okay, we choose this curve. It is the same curve, y equals square root of x, just written in terms of x equals something. We are revolving the same region that we used here, used in the previous example, the same region, not around y-axis, but around x-axis. Revolve around x-axis, so you can imagine what will happen, right? After you revolve it, you will obtain something like this, right? Of course, you can solve this volume question by using this method. Okay, let's first solve the same question by using this method, then we can discuss how to use Shell's method, right? Okay, so using this method, how do we solve it? So here is your thing. You have this region and you are revolving it around x-axis like this. This is the axis of revolution. So this was your region, and you look at the slices. They are full discs, right? The vertical slices. And maybe I should draw it better, like, okay. After you revolve it, so this is the cross sections for any arbitrary point x. You know, this curve is y equals square root of x. That's why the radius here is given by your curve directly. Okay, so the radius is square root of x much. So you are concentrating on this discs. And the points here, this is the point 0, this is the point 4. So the volume is a of x dx, where you will integrate a of x from 0 to 4, from here to here. So what is a of x? A of x is the area of this disk. So a of x is in fact pi radius x squared. So it is pi, radius is given by the curve, square root of x squared. Okay, that's why by using this method, this example is so simple like this. Pi And from 0 to 4 pi x dx, so integrate, it is pi times x squared over 2, then you will insert upper lower bounds, take the difference and find the result as 8 pi. Okay, this is how you find the volume of the solid object obtained by rotating this region around x-axis. So this method works like this. On the other hand, you can also use cylindrical shells method. So let's try to understand cylindrical shells method on this question. So this time, okay, as you are revolving this region around x-axis like this, the cylinders will be not vertical but horizontal. How can you understand this? So every time you will be drawing this line parallel to axis of revolution. So you will draw a line. So let me say, draw a line parallel to axis of revolution and parallel, draw a line passing through your region, let's say. Okay, let me write it better. Draw a parallel line, okay, passing through your region, which is parallel to axis of revolution. To axis of revolution. What do I mean by this sentence? So this is our axis of revolution. So I draw a line passing through my region, which is parallel to axis of revolution, okay? So this line will be the height. Then the importance of this line is this line will be the height of your cylinder. That's how you draw your cylinders correctly for each example. Okay, this will be the height, so you just complete your cylinder having this as the height, okay? That's why your cylinders are not vertical but horizontal in this case. Okay, how cylindrical shells method work? You will be writing 2 pi times shell's radius. You see, we covered it here, times shell's height, and then the boundaries on the axis of revolution. So what is the shell's radius here? This is some arbitrary point x, and this part is the radius for your, okay, maybe I can draw it better. Okay, this is the center, and this is the radius, okay? Radius of your cylinder for an arbitrary point x. The radius is given by this curve, right? The radius, okay, is given by this curve. And look at your curve. It is y equals square root of x. But this time, as your cylinders will cover each other through y-axis, everything will be written with respect to y. Okay, this is something important, okay? Shell's radius, shell's height. Okay, you will always be using this formula, but you have to recognize something before you express r and h. You need to understand whether the integral is with respect to dx or dy. So in this case, it is with respect to dy because, as you imagine, all the cylinders are covering each other, surrounding each other through y-axis. So everything will be with respect to y. That's why the radius here, if you solve this radius in terms of y, you will find, so solve x here in terms of y, right? X is y, just a second, let me use other colors. Okay. In fact, the radius is already this part, right? Y. And now we will find the height of this cylinder. So this is, as you can see from the picture, for any arbitrary y point, the radius is y. Okay, now what is the height? Height is this length. You see this length. So to find the height, in fact, what I need to do is from here to here, this is something fixed for, it is 4. And from here to here, you know, I name this point as x, but if I take the difference 4, then this part, I will find the height. This part is my height. What is it in terms of y? That's why I need to express this x point in terms of y, and it is related to our curve. For some arbitrary y on y-axis, this x hitting point is y. You can solve x here in terms of y as y squared. That's why this point is y squared on x-axis. And that's why the height is given by this whole length minus this much, which is y squared. Okay, that's how you should find your height. Then I can construct the expression here. It is solved as 4 minus y squared. So the integral is, now let's look at the boundaries on y-axis because you are writing the integral with respect to y. So the boundaries are from 0 to 2. 0 to 2. 2 pi is something fixed in the formula, and radius is already y, and height is solved as 4 minus y squared dy. Okay, if you compute this integral, it is not that difficult. You can take 2 pi out, just do this multiplication, 4y minus y cubed dy. So 2 pi 4y squared over 2 minus y to the power over 4. You see, I add 1 to the power divided by the same power. And then if you evaluate this expression between 2 and 0, you will obtain the same result as you did here, because no matter which method you use, disk or cylindrical shells, you are computing the volume of the same three-dimensional object. And here we studied cylindrical shells method with respect to y component. That's why we try to express everything, the radius and the height, in terms of y. Okay, so that's it. I stop here after looking at this summary. So how do you apply cylindrical shells method? You draw your region, of course, and then draw a line segment passing through your region parallel to axis of revolution that I emphasized above. This line segment will tell you the height of, will give you the height of your cylindrical shells. Okay, then you will find the height and find the radius of your cylindrical shell, and then you will be using this h and r in your volume formula, like 2 pi r h. It will be either with respect to dx or with respect to dy. It will change question to question. Then you will find the boundaries for your integration. And then, so this is what you are integrating here. Shell's radius, shell's height, like this too. Then you will compute the integral to find the volume. And this picture shows you very nicely how do we slice our three-dimensional object by using very thin cylindrical shells. So they are kind of like a paper roll, and it is possible to cover the whole volume by using these cylindrical shells.